The Multiverse, Parallel Universes and Alternate Realities. Part 1. Look up at the night sky. On a clear evening, away from the lights of cities, thousands of stars become visible. Each one seems distant, silent, almost eternal. For most of human history, people believed those stars were the entire universe. Everything that existed. Everything that ever would exist. Today, we know something astonishing. Those stars are only a tiny fraction of our own galaxy. The Milky Way alone contains hundreds of billions of stars. Beyond it lie hundreds of billions of other galaxies. And beyond those, the universe may continue farther than we can possibly observe. Yet modern physics asks an even more extraordinary question. What if our universe is not the only one? What if countless other universes exist beyond our own? Some nearly identical to ours. Others radically different. Some where history unfolded differently. Some where the laws of physics themselves are unlike anything we can imagine. This breathtaking possibility has become known as the multiverse. It is one of the most fascinating and controversial ideas in modern science. Unlike many popular mysteries, the multiverse did not originate in science fiction. Nor did it begin as a philosophical fantasy. Instead, it emerged naturally from several independent areas of modern physics: cosmology, quantum mechanics, inflation theory, string theory. Each, in its own way, hints that reality may be vastly larger than the single universe we experience. Whether those hints ultimately prove correct remains unknown. But the journey toward the multiverse begins long before modern science. Long before telescopes. Long before mathematics. Long before anyone knew that Earth was a planet orbiting a star. Human beings have always imagined worlds beyond their own. Ancient civilizations filled their stories with hidden realms. Invisible kingdoms. Parallel worlds existing alongside everyday reality. Although these stories were spiritual rather than scientific, they reveal something remarkable. Across continents separated by oceans, people imagined realities existing beyond ordinary perception. The ancient Egyptians believed the soul journeyed through the duat after death, a mysterious realm existing beyond the visible world. Greek mythology described Mount Olympus, the underworld, the Elysian fields, separate realms inhabited by gods, heroes, and the dead. Norse mythology spoke of the 9 realms connected by the great cosmic tree Yggdrasil. Among them were Asgard, Midgard, Jotunheim, Helheim. Each represented a different world existing simultaneously. In Hindu philosophy, the universe contains numerous planes of existence. Different realms occupied by gods, celestial beings, and human souls. Some traditions describe vast cosmic cycles lasting billions of years, during which universes are continually created and destroyed. Buddhist cosmology likewise envisions countless world systems existing throughout an immense cosmos. Many indigenous traditions also describe unseen spiritual worlds existing alongside the physical one. Although these ancient beliefs differ greatly from modern scientific theories, they reveal a common human instinct. The visible world has rarely been considered the whole story. People have always sensed that reality might extend beyond ordinary experience. As civilization advanced, philosophers began asking similar questions through reason rather than mythology. Around the 4th century BC, the Greek philosopher Democritus proposed an astonishing idea. If atoms move endlessly through infinite space, why should there be only one world? Perhaps countless worlds exist. Some inhabited, some barren, some larger than ours, others smaller. It was a breathtaking thought. More than 2,000 years before modern astronomy, Democritus imagined something remarkably similar to today's discussions of multiple worlds. Later, the Roman philosopher Lucretius expanded upon the idea. In his epic poem De Rerum Natura, he argued that an infinite universe should naturally contain countless other worlds. If nature possesses unlimited space and unlimited time, why would creation stop with only one universe? No evidence supported these ideas. They were philosophical arguments. Yet they demonstrated extraordinary imagination. Centuries later, another thinker would pay dearly for entertaining similar possibilities. His name was Giordano Bruno. Born in Italy during the 16th century, Bruno believed the universe contained infinitely many stars, each potentially surrounded by planets like Earth. He suggested that countless inhabited worlds might exist. These ideas challenged prevailing religious beliefs of the time. Eventually, Bruno was arrested by the Roman Inquisition. After years of imprisonment, he was executed in 1600. Although Bruno's execution involved multiple theological disputes beyond astronomy alone, he later became a symbol of intellectual freedom and humanity's willingness to question accepted ideas. Ironically, only a few years later, telescopes began transforming astronomy forever. Galileo Galilei pointed his telescope toward the heavens. He discovered mountains on the moon, moons orbiting Jupiter, phases of Venus. The universe proved far more complicated than anyone had imagined. Earth was no longer the center of creation. Humanity occupied only one small world among many. Over the next several centuries, astronomy continued expanding the known universe. William Herschel mapped stars throughout the Milky Way. Edwin Hubble later demonstrated that our galaxy was only one among countless others. Each discovery made the cosmos larger, older, more astonishing. Yet one assumption remained. There was still only one universe. Then, during the 20th century, modern physics began revealing something unexpected. The universe itself appeared stranger than anyone anticipated. Albert Einstein showed that space and time formed a single fabric called spacetime. Gravity bent that fabric. Black holes distorted it. Quantum mechanics introduced uncertainty, probability, particles behaving like waves. Reality no longer resembled the predictable machine imagined by 19th century science. Instead, nature became deeply mysterious. The deeper physicists explored. The stranger reality appeared. Some interpretations of quantum mechanics suggested multiple histories. Cosmologists studying the Big Bang discovered models naturally producing many universes rather than one. String theory introduced enormous numbers of possible cosmic configurations. Suddenly, the multiverse was no longer merely philosophy. It had become a legitimate scientific possibility. Not a proven fact, but a serious hypothesis emerging from mathematics itself. It is important to understand exactly what scientists mean by the word multiverse. Popular culture often imagines alternate Earths existing beside our own. Another version of you. Another version of history. A world where dinosaurs never became extinct. Or where ancient Rome never fell. These ideas make compelling stories. Some scientific theories resemble them. Others describe something entirely different. Some multiverse models involve regions forever beyond our observable universe. Others involve quantum branching realities. Still others suggest entirely separate universes possessing different physical laws. The word multiverse actually refers to several very different ideas, each arising from different branches of physics, each carrying different implications. Throughout this journey, we will explore them one by one, separating established science from speculation, mathematics from imagination, evidence from possibility. Because the multiverse remains one of the greatest unanswered questions in modern science. No telescope has photographed another universe. No spacecraft has visited one. No experiment has conclusively demonstrated their existence. Yet some of the finest scientific minds in history have taken the idea seriously. Not because they wished reality to become stranger, but because their equations repeatedly pointed in that direction. Whether those equations ultimately describe nature remains unknown. The search continues. And like every great scientific mystery, it begins with a simple question. How big is our universe, really? Because before we can ask whether other universes exist, we must first understand the astonishing scale of the one we already inhabit. Part 2. If you could travel faster than light, past every planet in our solar system, beyond every nearby star, across the Milky Way, and continue for billions of years, would you eventually reach the edge of the universe? At first glance, the answer seems obvious. Everything should have an edge. Continents end. Oceans end. Clouds end. Even galaxies have boundaries. Surely the universe must end somewhere. Surprisingly, modern science does not know. One of the greatest misconceptions in astronomy is the idea that the observable universe and the entire universe are the same thing. They are not. The observable universe is simply the portion of the cosmos whose light has had enough time to reach Earth since the Big Bang. It is the limit of what we can currently see, not necessarily the limit of what exists. To understand why, imagine standing in the middle of a dense forest. Trees surround you in every direction. Because of the thick vegetation, you can see only a short distance. Does that mean the forest ends where your vision stops? Of course not. The forest may continue for miles beyond what you can observe. The observable universe works in much the same way. Light travels at a finite speed, approximately 300,000 kilometers every second. Although incredibly fast, light still requires time to cross enormous distances. The light from the moon reaches Earth in about 1.25 seconds. Sunlight requires roughly 8 minutes. The nearest star beyond our Sun, Proxima Centauri, lies more than 4 light-years away. Its light began traveling toward us over 4 years ago. When astronomers observe distant galaxies, they are literally looking into the past. A galaxy 1 billion light-years away appears as it existed 1 billion years ago. The farther we look, the farther back in time we see. The most distant light ever detected began its journey more than 13 billion years ago. It comes from an era shortly after the Big Bang itself. This ancient glow fills the entire sky. It is known as the cosmic microwave background. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, it represents the oldest light humanity has ever observed. The discovery transformed cosmology. It confirmed that the universe was once much hotter and denser than it is today. The cosmic microwave background became one of the strongest pieces of evidence supporting the Big Bang. Yet it also revealed something remarkable. The observable universe possesses a finite size. Not because the universe necessarily ends there, but because light has had only a finite amount of time to reach us. Today, the observable universe stretches approximately 93 billion light-years across. That number surprises many people. If the universe is only about 13.8 billion years old, how can the observable universe be 93 billion light-years wide? The answer lies in cosmic expansion. Space itself has been stretching since the Big Bang. Galaxies are not simply moving through space. Space between galaxies is expanding. Imagine drawing dots on the surface of a balloon. As the balloon inflates, every dot moves farther from every other dot. None of the dots is actually traveling across the balloon's surface. The surface itself expands. Our universe behaves similarly. This remarkable discovery emerged during the 1920s through the work of American astronomer Edwin Hubble. Using powerful telescopes, Hubble examined distant galaxies. He noticed something extraordinary. Almost every galaxy appeared to be moving away from us. The farther away a galaxy was, the faster it seemed to recede. At first glance, this might suggest Earth occupies the center of the universe. It does not. Imagine raisins inside rising bread dough. As the dough expands, every raisin sees every other raisin moving away. No raisin occupies the center. Expansion occurs everywhere simultaneously. The universe behaves in much the same way. This discovery fundamentally changed cosmology. If the universe is expanding today, then reversing time suggests it was once much smaller, hotter, denser. Eventually, scientists concluded that the observable universe began approximately 13.8 billion years ago in an event now known as the Big Bang. Contrary to popular belief, the Big Bang was not an explosion occurring within empty space. It was the rapid expansion of space itself. There was no center from which galaxies exploded outward. Every region of today's observable universe emerged together. The Big Bang marks the beginning of our observable cosmic history. Yet another fascinating question soon emerged. What happened before the Big Bang? Modern physics cannot yet answer with certainty. Some theories suggest time itself began with the Big Bang. Others propose earlier phases of cosmic evolution. Still others describe an eternal process producing countless universes. These ideas remain speculative. Nevertheless, they illustrate how quickly cosmology reaches the limits of current knowledge. As astronomers measured the universe more precisely, another mystery appeared. The expansion was not slowing down. It was accelerating. This astonishing discovery earned the 2011 Nobel Prize in Physics. Something unseen seemed to be pushing galaxies apart. Scientists named the mysterious phenomenon dark energy. Today, dark energy appears to make up roughly 68% of the universe. Dark matter contributes another 27%. Ordinary matter, the stars, planets, gas, dust, and everything visible, accounts for only about 5%. In other words, everything humanity has ever directly observed represents only a tiny fraction of reality. Most of the universe remains invisible. We know it exists because of its gravitational effects and influence on cosmic expansion. We do not yet know what it actually is. This realization has profound implications. If 95% of reality remains mysterious, perhaps our understanding of the cosmos remains only beginning. Some physicists compare current cosmology to studying an enormous library while reading only a few pages. We have learned a tremendous amount. Yet vastly more remains unknown. Another important concept concerns the shape of the universe. Is space curved like the surface of a sphere? Does it resemble a saddle? Or is it perfectly flat? Satellite missions such as WMAP and Planck have measured the cosmic microwave background with extraordinary precision. Their observations suggest that the observable universe is remarkably close to geometrically flat. Why does this matter? Because a flat universe may extend infinitely. Imagine standing on an endless plain. No matter how far you travel, the landscape continues. Similarly, if space is truly flat and infinite, there may be no edge at all. The observable universe would then represent only a tiny patch within an unimaginably larger cosmos. And if the universe is infinite, an astonishing possibility follows. Every physically possible arrangement of matter must eventually repeat. Somewhere, unimaginably far away, there could exist another Earth, another solar system, another Milky Way, perhaps even another version of you. Not because of quantum mechanics, not because of alternate dimensions, simply because infinite space eventually repeats finite patterns. This idea forms the basis of one category of multiverse theory, known as the Level 1 multiverse. It does not require exotic new physics, only an infinite universe. Whether space truly extends forever remains unknown. Current observations cannot see beyond the observable horizon. The universe may indeed be infinite, or merely so vast that its curvature remains undetectable. Either possibility remains consistent with modern observations. Already, reality has become almost impossible to comprehend. A universe 93 billion light-years across, containing hundreds of billions of galaxies, each holding hundreds of billions of stars. Most of it composed of mysterious substances we cannot directly observe. possibly extending forever beyond our view. Yet astonishingly, some physicists believe this may represent only one universe among many. To understand why, we must travel back to the first tiny fraction of a second after the Big Bang, when the infant universe experienced one of the most extraordinary events in cosmic history. An event known as cosmic inflation. And according to some of the most successful models in modern cosmology, inflation may never have truly ended. Part 3. Imagine blowing up a balloon. At first, it expands slowly. Then, with each breath, it grows larger and larger. Now imagine something even more extraordinary. A balloon that expands from smaller than an atom to larger than an entire galaxy. In less than the blink of an eye. As impossible as it sounds, many cosmologists believe something very much like this happened during the earliest moments of our universe. This event is known as cosmic inflation. Today, inflation is one of the most influential ideas in modern cosmology. It was proposed in 1980 by American physicist Alan Guth. At the time, the Big Bang theory had become widely accepted. It successfully explained many observations. The expansion of the universe. The abundance of light elements. The cosmic microwave background. Yet several important puzzles remained. One of the biggest was known as the horizon problem. To understand it, imagine placing 2 cups of coffee on opposite sides of a large room. Without allowing them to interact, they somehow cool to exactly the same temperature. That would seem highly unlikely. Yet something very similar appeared in the universe. When astronomers measured the cosmic microwave background, they discovered that regions of space separated by enormous distances possessed almost exactly the same temperature. The difference was incredibly tiny. Less than 1 part in 100,000. According to the original Big Bang model, those distant regions had never been close enough to exchange heat or information. So how had they become so similar? Inflation offered an elegant solution. Before the rapid expansion, the entire observable universe occupied an extraordinarily tiny region. Everything had plenty of time to reach the same temperature. Then, suddenly, space expanded at an astonishing rate. Regions once close together became separated by billions of light years. Like raisins carried apart by rapidly rising bread dough. They retained their nearly identical temperatures even after becoming enormously distant. Another puzzle involved the shape of the universe. As discussed previously, observations indicate that space appears remarkably flat. This created the flatness problem. Imagine balancing a pencil perfectly upright on its tip. The slightest disturbance causes it to fall. Similarly, the early universe would have required astonishingly precise conditions to remain nearly flat for billions of years. Inflation solved this mystery as well. Imagine standing on Earth's surface. From ground level, the Earth appears flat. Only from space does its curvature become obvious. Now imagine inflating Earth until it becomes millions of times larger. The tiny area beneath your feet would appear even flatter. Likewise, inflation stretched any initial curvature until the observable universe became almost perfectly flat. The theory also explained why no exotic magnetic monopoles had ever been observed, despite predictions from some particle physics models. 3 major cosmological puzzles suddenly acquired one elegant explanation. The scientific community quickly took notice. During the following decades, increasingly precise observations strengthened inflation's reputation. Satellite missions measured the tiny temperature fluctuations in the cosmic microwave background. These patterns matched predictions made by inflation remarkably well. Today, while details continue being refined, inflation remains one of the leading descriptions of the universe's earliest moments. Then physicists noticed something astonishing. The mathematics suggested that inflation might not stop everywhere simultaneously. Imagine boiling water in a pot. Bubbles form randomly. Some grow. Others disappear. The boiling continues. Now imagine replacing water with space itself. Instead of bubbles of steam, tiny regions stop inflating and become individual universes. Meanwhile, surrounding space continues expanding. New bubbles form endlessly. Each bubble becomes its own universe. This remarkable concept became known as eternal inflation. According to this idea, our universe represents only one bubble among an unimaginably vast cosmic foam. Inflation never completely ends. It continues forever in distant regions beyond our observable horizon. As old bubble universes drift apart, new ones continually emerge. Each may possess its own history, its own galaxies, perhaps even its own physical laws. This concept gave birth to what cosmologists call the Level 2 multiverse. Unlike the Level 1 multiverse, which simply extends our own universe farther than we can observe, the Level 2 multiverse proposes entirely separate universes, each born from eternal inflation. These universes would remain forever isolated from one another. The expanding space between them grows so rapidly that communication becomes impossible. No spacecraft could ever cross the gap. No signal could reach another bubble. Each universe effectively becomes its own independent cosmos. One fascinating implication concerns the laws of physics themselves. In our universe, gravity possesses a particular strength. Electrons have specific masses. The speed of light remains constant. Certain nuclear reactions produce stars, atoms, planets, life. But what determines these values? Why is gravity exactly as strong as it is? Why not slightly stronger? Or weaker? Current physics cannot answer completely. Some versions of eternal inflation suggest that different bubble universes naturally acquire different physical properties. In one universe, gravity might be much stronger. Stars could burn too quickly for life to evolve. In another, gravity might be too weak for galaxies to form. Some universes may contain no chemistry at all. Others might collapse almost immediately after their birth. A few, perhaps extraordinarily rare, possess just the right conditions for complexity and life. This idea connects with another philosophical concept called the anthropic principle. At first, the principle sounds almost trivial. It states that we observe a universe compatible with life because otherwise we would not be here to observe it. Suppose billions, or even infinitely many, universes exist. Most remain sterile. A few permit galaxies. A smaller number allow planets. An even smaller fraction support life. Observers inevitably find themselves in one of those rare life-friendly universes. The anthropic principle does not prove the multiverse. Rather, it explains why, if many universes exist, ours appears unusually well suited for life. Some physicists find this reasoning compelling. Others argue that it explains too much while predicting too little. The debate remains active. Another important prediction of eternal inflation concerns collisions. If bubble universes occasionally formed close together, they might briefly collide during their earliest moments. Such collisions could leave subtle patterns within the cosmic microwave background. Astronomers have searched carefully for these signatures. Thus far, no convincing evidence has been found. Several intriguing features have been investigated. None has achieved broad scientific acceptance. Still, the search continues. Future observations may provide greater sensitivity, perhaps one day revealing evidence impossible to explain any other way. Or perhaps showing that our universe evolved entirely alone. Either outcome would profoundly influence cosmology. It is worth emphasizing something important. Inflation itself enjoys substantial observational support. Eternal inflation is more speculative. The mathematics permits it. Some versions of inflation naturally produce it. Other models do not. Scientists continue debating which description most accurately reflects reality. This distinction between well-supported theory and speculative extension is one of science's greatest strengths. Ideas earn acceptance through evidence, not popularity, not elegance alone. As remarkable as inflation appears, another branch of physics independently arrived at an even more astonishing possibility. Not through cosmology, but through quantum mechanics. A theory suggesting that every quantum event may create new realities. Not bubble universes scattered across cosmic distances, but countless branching histories emerging every moment. A universe where every possibility actually happens. This extraordinary proposal became known as the many worlds interpretation. And for many people, it represents the most fascinating multiverse theory ever conceived. Part 4. If cosmic inflation suggests that countless universes may exist far beyond our reach, quantum mechanics proposes something even stranger. Perhaps new realities are constantly being created. Right here. Every second. With every quantum event. To understand this astonishing possibility, we must first enter the microscopic world. A world where ordinary intuition begins to fail. Imagine shrinking until you are smaller than an atom. Smaller than an electron. At this scale, the familiar rules governing everyday life no longer seem to apply. Objects do not behave like tiny billiard balls. Instead, they exist as clouds of probability. Particles sometimes behave like waves. Waves sometimes behave like particles. Events occur that appear almost impossible. Yet every experiment confirms the same conclusion. Nature truly works this way. The story begins early in the 20th century. Scientists studying atoms quickly realized that classical physics could no longer explain what they observed. Electrons refused to orbit atoms like planets circling the sun. Light behaved in contradictory ways. Tiny particles displayed surprisingly unpredictable behavior. One experiment became especially famous: the double-slit experiment. Although simple in design, it has become one of the most important experiments in the history of science. Imagine a solid barrier containing two narrow openings. Behind the barrier stands a screen capable of recording tiny impacts. Now fire small particles, perhaps electrons, toward the slits. Common sense predicts a straightforward result. Particles passing through the left slit should create one band. Particles passing through the right slit should create another. Instead, something astonishing appears. An interference pattern. The same pattern produced by overlapping water waves. It is as though each individual particle somehow travels through both slits simultaneously, interfering with itself. The mystery deepens further. Suppose scientists place detectors beside the slits to determine which opening each particle actually uses. The interference pattern disappears. The particles suddenly behave exactly as ordinary objects should. One slit. One path. One impact. Remove the detectors. The wave pattern returns. For more than a century, physicists have debated what this remarkable experiment truly means. The mathematics predicts the results perfectly. Interpreting those results remains another matter entirely. The traditional explanation became known as the Copenhagen interpretation. Developed primarily by Niels Bohr and Werner Heisenberg, it proposes that quantum systems exist as probabilities until measurement occurs. Before observation, the particle possesses multiple possible outcomes. Measurement somehow forces one outcome to become reality. Exactly what constitutes a measurement remains surprisingly subtle. Does it require a conscious observer? Most physicists today answer no. Measurement generally involves interaction with the surrounding environment rather than human awareness. Nevertheless, the philosophical questions remain profound. In 1935, Austrian physicist Erwin Schrödinger introduced one of the most famous thought experiments ever conceived. He imagined placing a cat inside a sealed box. Alongside the cat sits a tiny amount of radioactive material. If one atom decays, it triggers a mechanism releasing poison. If the atom does not decay, the cat survives. According to quantum mechanics, before the box is opened, the atom exists in a superposition of possibilities. Schrödinger asked a provocative question. Does that mean the cat is somehow both alive and dead until observed? Of course, Schrödinger did not believe real cats literally exist in both conditions simultaneously. The thought experiment highlighted how strange quantum ideas become when extended into everyday life. It exposed the difficulties involved in interpreting quantum mechanics. The mathematics worked beautifully. Understanding what the mathematics meant proved much harder. Then, in 1957, a young American physicist named Hugh Everett III proposed a radical alternative. Everett disliked the idea that observation somehow collapses probabilities into reality. He wondered whether collapse occurs at all. Suppose every possible outcome actually happens. Instead of one possibility becoming real, the universe itself branches. Imagine standing at a crossroads. One road turns left. The other turns right. In everyday experience, you choose one direction. Everett suggested something extraordinary. Perhaps both choices occur. The universe splits. One version of you walks left. Another walks right. Neither version realizes the branching occurred. Each experiences only its own history. This idea became known as the many worlds interpretation. According to Everett, every quantum event creates additional branches of reality. Whenever multiple outcomes are possible, all occur, each within its own universe. The branching happens continuously. Every radioactive decay, every photon interaction, every quantum event throughout the cosmos. Reality constantly divides into an unimaginably vast number of parallel histories. Unlike science fiction, these parallel worlds do not float beside one another waiting to be visited. Once branches separate, they no longer interact in ordinary circumstances. Each follows its own independent history. You remain aware only of the branch you experience. This interpretation possesses one remarkable advantage. It removes the mysterious idea of wave function collapse. The mathematics evolves smoothly at all times. Nothing special happens during measurement. Instead, observers themselves become part of the branching process. Many physicists appreciate this mathematical elegance. Others find the implications almost impossible to accept. After all, if every quantum event creates new universes, how many universes exist? The answer becomes almost unimaginable. Not billions. Not trillions. Potentially an effectively limitless number. Every possible history consistent with quantum mechanics unfolds somewhere. In one universe, a coin lands heads. In another, tails. In one, dinosaurs become extinct. In another, if physically possible, they survive. Some branches differ only microscopically. Others eventually diverge dramatically. Popular culture quickly embraced these ideas. Movies portrayed alternate versions of familiar characters. Television series explored branching timelines. Comic books filled entire libraries with parallel Earths. The Marvel and DC universes introduced audiences to countless alternate realities. Although entertaining, these stories often simplify or exaggerate the underlying physics. The many worlds interpretation does not currently suggest that people can consciously move between branches. Nor does it predict spontaneous meetings between alternate versions of ourselves. Those ideas belong primarily to fiction. Even within physics, many worlds remains only one interpretation among several. Importantly, all major interpretations of quantum mechanics make essentially identical experimental predictions. Whether reality truly branches or probabilities collapse, current experiments generally cannot distinguish between them. This creates one of the most unusual situations in science. Different philosophical interpretations produce the same observable results. The mathematics remains unchanged. Only the explanation differs. Some physicists embrace many worlds enthusiastically. Others prefer the Copenhagen interpretation. Still others support alternatives such as objective collapse theories or pilot wave theory. The debate continues. Perhaps future experiments will eventually distinguish among them. Perhaps not. One fascinating consequence of many worlds concerns identity itself. Suppose countless versions of you exist, each making different choices, each living different lives. Are they truly you? Or entirely separate individuals sharing a common past? Philosophers continue debating these questions. The answers remain deeply uncertain. Yet they illustrate how profoundly quantum mechanics challenges ordinary concepts of self and reality. Remarkably, the multiverse does not end there. Another influential branch of theoretical physics proposes something even more extraordinary. Perhaps universes differ not only in their histories, but in the very laws of physics themselves. Gravity, light, matter, space, time, all could vary from one universe to another. This breathtaking possibility emerges from one of the most ambitious attempts ever made to unify all of physics, a framework known as string theory. Part 5. Imagine listening to an orchestra. Violins, cellos, trumpets, flutes. Every instrument produces a different sound. Yet each note begins the same way. A vibration. Now imagine that the smallest building blocks of the universe behave similarly. Instead of tiny point-like particles, perhaps everything is made from unimaginably small vibrating strings. Different vibrations create different particles. One vibration becomes an electron. Another becomes a quark. Another becomes a photon. This extraordinary idea forms the foundation of string theory. For decades, string theory has represented one of the most ambitious attempts to answer a question that has challenged physicists for generations. Can all the forces of nature be explained by one elegant theory? Today, modern physics rests upon two magnificent achievements. The first is general relativity, Einstein's masterpiece describing gravity, planets, stars, black holes, galaxies, the evolution of the universe itself. The second is quantum mechanics, the theory governing atoms, electrons, photons, nuclear reactions, everything occurring at microscopic scales. Each theory works extraordinarily well. Together, they explain nearly every experiment ever performed. Yet there is a problem. The two theories refuse to fit together. When physicists attempt to describe gravity using quantum mechanics, the mathematics breaks down. Likewise, general relativity cannot fully explain quantum phenomena. Somewhere, a deeper theory almost certainly exists. String theory attempts to provide that missing connection. According to the theory, particles are not infinitely small points. Instead, they are tiny one-dimensional strings. These strings are unimaginably small, far smaller than anything current technology can directly observe. The different ways they vibrate determine the properties of matter. Just as different musical notes arise from different vibrations of a violin string, different elementary particles arise from different vibrations of fundamental cosmic strings. The mathematics proved surprisingly powerful. Even more remarkably, gravity appeared naturally. Unlike previous attempts, string theory automatically predicted a particle carrying gravity, known as the graviton. No experiment has yet detected gravitons. Nevertheless, their appearance within the equations encouraged physicists that they might be moving in the right direction. Then came another surprise. The mathematics would not work in only 3 dimensions of space, nor even 4 dimensions of spacetime. Instead, string theory required additional dimensions. Some versions demanded 10 dimensions. Others required 11. At first, this sounded absurd. Where are these hidden dimensions? Why don't we see them? Physicists proposed that the extra dimensions are curled into unimaginably tiny shapes. Imagine looking at a garden hose from a great distance. It appears one-dimensional. A simple line. Walk closer. A second dimension becomes visible. The hose has thickness. Similarly, the additional dimensions predicted by string theory may exist at scales so incredibly small that they escape direct observation. Although invisible, these hidden dimensions could profoundly influence the behavior of particles and forces. As researchers explored the equations more deeply, another remarkable discovery emerged. There was not just one solution. There were an enormous number of possible solutions, each describing a different universe, different physical constants, different particles, different forces, different dimensions. Early hopes that string theory would uniquely describe our universe gradually faded. Instead, the theory appeared to predict a vast landscape of possible universes. This became known as the string landscape. Some estimates suggest the number of mathematically possible universes may exceed 10 to the power of 500. That is the number 1 followed by 500 zeros. A quantity so unimaginably large that it exceeds ordinary human comprehension. Each solution corresponds to a different vacuum state, a different way the hidden dimensions might be folded. Different folding patterns produce different laws of physics. In one universe, gravity might be stronger. In another, weaker. Some universes may possess 4 large spatial dimensions. Others perhaps only 2. Some might never form stars. Others may collapse almost instantly. Only a tiny fraction appear capable of producing galaxies, planets, chemistry, and eventually life. This idea connected naturally with eternal inflation. If inflation continually creates new bubble universes, perhaps each bubble settles into a different string theory solution. Instead of one universe, reality becomes a cosmic landscape filled with extraordinary diversity. Together, eternal inflation and the string landscape form one of the most influential multiverse models discussed by modern cosmologists. Not because scientists have observed other universes, but because independent branches of theoretical physics unexpectedly point towards similar possibilities. Still, many physicists remain cautious. String theory has achieved remarkable mathematical success. Yet no direct experimental evidence currently confirms it. Particle accelerators have not detected strings. Extra dimensions remain unobserved. The theory continues evolving. Some researchers remain optimistic. Others have shifted toward competing approaches. One alternative is loop quantum gravity. Rather than introducing strings, loop quantum gravity attempts to quantize spacetime itself. According to this view, space is not infinitely smooth. Instead, it may consist of incredibly tiny discrete units, almost like individual threads woven together into a cosmic fabric. Although mathematically very different from string theory, loop quantum gravity shares the same goal: uniting gravity and quantum mechanics into one consistent description. Another fascinating proposal comes from physicist Max Tegmark. He developed what he calls the mathematical universe hypothesis. Tegmark argues that mathematics is not merely a language humans invented to describe reality. Instead, reality itself is mathematics. If every mathematically consistent structure exists, then every mathematically possible universe exists as well. This concept became known as the level 4 multiverse. Among all multiverse theories, it is perhaps the most abstract. It suggests that every internally consistent mathematical universe possesses physical existence. Many physicists regard the idea as highly speculative. Others consider it a logical extension of mathematical realism. Whether correct or not, it illustrates how deeply multiverse discussions intersect with philosophy. The deeper scientists investigate reality, the more difficult it becomes to separate physics from metaphysics. This raises another profound question. If countless universes exist, could another version of you exist somewhere among them? Not merely someone similar, but another individual sharing your memories, your appearance, your life. A version whose history diverged from yours because of one small decision. One different choice. One tiny event. For many people, this possibility captures the imagination more than any equation ever could. It transforms the multiverse from abstract cosmology into something intensely personal. Could another Earth exist? Another civilization? Another humanity? Perhaps somewhere. Another version of you is wondering exactly the same thing. The next chapter explores this remarkable possibility and asks what parallel universes might mean for identity, free will, and the countless lives we might have lived. Part 6. Imagine waking tomorrow morning. Everything appears familiar. The same home. The same family. The same memories. The same world. But somewhere beyond the limits of your perception, another version of you also awakens. They remember the same childhood, the same friends, the same experiences, until one moment, one decision, one tiny event changed everything. From that point onward, your lives slowly began to diverge. One became a scientist, the other an artist. One moved across the country. The other never left home. One met different friends, made different choices, lived a different life. Could such alternate versions of ourselves actually exist? The answer depends entirely upon which multiverse theory one considers. In the Level 1 multiverse, if space truly extends infinitely, every physically possible arrangement of matter should eventually repeat. Given enough distance, atoms would inevitably arrange themselves into patterns nearly identical to those found on Earth. Somewhere beyond our observable horizon, there could exist another planet almost indistinguishable from our own. Another solar system. Another Milky Way. Eventually, another Earth. And perhaps another version of you. Not because reality branched. Not because time changed. Simply because infinite space allows every finite arrangement to occur again. The distances involved, however, are almost beyond imagination. Some estimates suggest such identical regions would lie so far away that no signal traveling at the speed of light could ever reach them. For all practical purposes, they remain forever inaccessible. The many worlds interpretation offers a different picture. Instead of distant copies arising through infinite space, alternate versions emerge whenever quantum events branch. Every possible outcome unfolds, each within its own history. In this view, alternate versions of you exist not because of distance, but because reality itself continually divides. These parallel lives may differ only slightly, or dramatically. Perhaps in one branch you chose a different career. In another, you met different friends. In another, history itself unfolded differently. Each branch represents a complete and internally consistent reality. Yet none can normally communicate with the others. This raises one of philosophy's oldest questions. What makes you? You? Is it your body? Your memories? Your experiences? If countless versions exist, which one is the real you? Many philosophers argue that each branch represents a genuinely distinct individual. Once histories diverge, identities gradually become unique. Although they share a common past, they become different people. This idea resembles identical twins. Twins share the same genetic blueprint. Yet their lives quickly become different through experience. Parallel versions of yourself would differ even more dramatically over time. Another fascinating question concerns free will. Do we truly choose our actions? Or does every possible decision occur somewhere? Suppose you stand before two doors. You must choose one. According to everyday experience, you select either the left door or the right. The unchosen possibility simply disappears. The many worlds interpretation suggests something very different. Perhaps both choices occur. One version of you opens the left door. Another opens the right. Each believes they freely chose their path. Each experiences only one outcome. Does this eliminate free will? Opinions differ. Some philosophers argue that each version still genuinely makes a choice. Others suggest branching changes our understanding of what choice means. The debate remains unresolved. Another concept frequently discussed is the butterfly effect. Originally developed within chaos theory, the butterfly effect describes how tiny changes can produce enormous consequences over time. The phrase comes from meteorologist Edward Lorenz, who suggested that the flap of a butterfly's wings might ultimately influence weather patterns weeks later. Whether literally true or not, the metaphor illustrates an important principle. Complex systems can become highly sensitive to small initial differences. Now imagine applying that idea to alternate histories. Suppose one tiny event changes. A delayed train. A missed phone call. A chance meeting. Over decades, that small difference might completely transform countless lives. History itself could unfold differently. Science fiction often explores this theme. In one timeline, an empire rises. In another, it falls. One scientific discovery occurs decades earlier. Another never happens. Entire civilizations follow different paths because of seemingly insignificant events. Although dramatic, these stories reflect genuine concepts from complexity science. Small changes can indeed produce surprisingly large consequences. One particularly intriguing question involves memory. If alternate versions of ourselves exist, could memories somehow pass between realities? Some supporters of paranormal explanations suggest phenomena like déjà vu or the Mandela effect represent brief glimpses into alternate timelines. Modern neuroscience offers more conventional explanations. Déjà vu appears related to temporary processing mismatches within memory systems. The Mandela effect can often be explained through false memories, pattern recognition, and social reinforcement. No experimental evidence currently demonstrates memories crossing between universes. Nevertheless, the idea continues capturing popular imagination. Perhaps because it offers an emotionally satisfying explanation for experiences that feel mysterious. Another topic frequently explored involves dreams. Some speculative theories suggest vivid dreams represent glimpses of parallel lives. Again, neuroscience provides more grounded explanations involving memory consolidation, emotional processing, and spontaneous brain activity during sleep. Scientists have found no evidence that dreams connect different universes. Yet the notion persists in literature, films, and philosophical discussions. One reason alternate selves fascinate us so deeply is psychological. They embody possibility. Every life contains unrealized paths. Careers never pursued. Places never visited. Relationships never begun. The multiverse transforms these unrealized possibilities into imagined realities. Somewhere, perhaps another version of ourselves experienced those alternate lives. Whether literally true or not, the idea encourages reflection. Who might we have become under different circumstances? History offers another perspective. Consider famous individuals. What if Isaac Newton had never developed calculus? What if Marie Curie had chosen another profession? What if the Apollo program had been cancelled before reaching the moon? Would someone else eventually achieve those breakthroughs? Would civilization progress differently? Counterfactual history explores such questions without requiring actual parallel universes. It reminds us that history often depends upon countless interconnected events. The multiverse simply extends this reasoning much further. Entire universes become alternate histories. Some almost identical. Others unimaginably different. Still, one important limitation remains. No known scientific theory currently allows communication between these alternate realities. No messages. No travel. No observations. At least according to our present understanding. If other universes exist, they appear isolated from our own. That isolation presents one of the greatest challenges facing multiverse research. How can scientists study something that may forever remain beyond direct observation? Remarkably, researchers are attempting exactly that. Rather than searching for portals, they search for subtle clues. Tiny fingerprints left behind during the birth of the universe. Patterns within ancient light. Invisible matter. Gravitational waves. And other phenomena that might reveal whether our universe truly shares reality with countless others. The search has already begun. And the next chapter explores the evidence scientists hope may one day answer one of humanity's greatest questions. Do other universes really exist? Part 7. For centuries, astronomers searched the skies for new planets. Then for distant galaxies. Today, some scientists are searching for something even more extraordinary. Evidence that our universe may not be alone. At first, this seems impossible. If other universes exist beyond our own, how could we ever detect them? After all, by definition, they lie outside our observable universe. No telescope can simply point toward another reality. No spacecraft can travel beyond the cosmic horizon. Yet science has surprised us before. Invisible objects are often discovered indirectly. No one has ever seen gravity itself. We observe its effects. Dark matter has never been directly detected. We infer its existence from how galaxies rotate. Even black holes remained invisible until astronomers observed the way they influence nearby stars and light. Perhaps the multiverse, if it exists, also leaves subtle fingerprints. The search begins with one of the oldest lights in existence. The cosmic microwave background, often called the CMB. As discussed earlier, this ancient glow fills the entire sky. It originated roughly 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely through space. Because it preserves a snapshot of the infant universe, cosmologists study it with extraordinary precision. Satellites such as COBE, WMAP, and later Planck measured tiny variations in the CMB's temperature. These differences are incredibly small. Only about 1 part in 100,000. Yet they contain a wealth of information. They reveal the seeds from which galaxies eventually formed. They confirm the predictions of cosmic inflation. They help determine the age, composition, and geometry of the universe. Some researchers have proposed that if another bubble universe collided with ours during the earliest moments after the Big Bang, the collision might have left a faint circular imprint within the CMB. Astronomers have searched carefully for such patterns. Several possible candidates have occasionally attracted attention. So far, however, none has provided convincing evidence. Most apparent anomalies eventually prove consistent with ordinary statistical fluctuations. The search continues. Another promising avenue involves gravitational waves. Predicted by Einstein in 1916 and first directly detected in 2015, gravitational waves are ripples in spacetime produced by accelerating massive objects. When two black holes collide, space itself vibrates. Sensitive instruments known as LIGO and Virgo can measure these tiny distortions. Future generations of gravitational wave detectors may become vastly more sensitive. Some cosmologists hope they might eventually detect signals originating from the earliest fractions of a second after the Big Bang. Those signals could reveal whether inflation occurred exactly as predicted. They might even provide indirect clues about eternal inflation and the existence of other bubble universes. Again, no such evidence currently exists. But the possibility remains scientifically interesting. Then there is the enduring mystery of dark matter. Astronomers first realized something unusual while studying the motion of galaxies. Stars orbit the centers of galaxies far faster than visible matter alone should allow. According to Newtonian gravity, many galaxies ought to fly apart. Instead, they remain intact. Something invisible appears to supply additional gravity. Scientists named this unseen substance dark matter. Despite decades of research, no one yet knows what dark matter actually is. Numerous possibilities have been proposed. Weakly interacting massive particles. Axions. Sterile neutrinos. Entirely new particles beyond the standard model. Some highly speculative ideas even suggest that gravitational effects from neighboring universes could influence our own. Most physicists consider this unlikely. Current evidence favors more conventional explanations involving new forms of matter. Nevertheless, the mystery remains one of modern science's greatest unsolved problems. Dark energy presents an equally profound puzzle. In 1998, astronomers discovered that the expansion of the universe is accelerating. Some unknown influence appears to be pushing galaxies apart. Dark energy now seems to comprise nearly 70% of the cosmos. Its true nature remains unknown. Whether dark energy connects in any way to multiverse theories is still an open question. Some cosmological models suggest that different universes may possess different amounts of vacuum energy. Others do not. At present, observations cannot distinguish between these possibilities. Another fascinating area of investigation involves particle physics. Facilities such as CERN continue searching for new particles beyond the standard model. Some theories involving extra dimensions predict that high-energy collisions might produce subtle signatures. Missing energy. Unexpected decay patterns. Previously unknown particles. These observations would not directly prove the multiverse, but they could support broader theoretical frameworks, such as string theory, from which certain multiverse models arise. Again, no confirmed discoveries have yet pointed in that direction. Perhaps the greatest challenge facing multiverse research is something philosophers call falsifiability. The concept was championed by philosopher of science Karl Popper. A scientific theory should, in principle, be testable. It should make predictions that could eventually prove it wrong. If no possible observation can distinguish a theory from every alternative, many scientists argue it lies outside empirical science. This criticism has been directed towards several multiverse proposals. If other universes remain forever beyond observation, can their existence truly be tested? Supporters respond that some multiverse models do make indirect predictions. Inflation predicts observable features. String theory seeks measurable consequences. Future discoveries may support or contradict these frameworks. The debate remains active. Importantly, scientists do not all agree. Some leading cosmologists consider the multiverse a natural extension of existing theories. Others believe it introduces unnecessary assumptions. Still others argue that entirely new ideas may eventually replace current models. This diversity of opinion is healthy. Science advances through evidence, discussion, and continual revision, not through unanimous agreement. Meanwhile, technology continues improving. The James Webb Space Telescope is already revealing galaxies that formed astonishingly early in cosmic history. Future observatories may probe even deeper into the universe's infancy. New particle accelerators may uncover previously unknown physics. More sensitive gravitational wave detectors may open entirely new windows on the cosmos. Each advance brings opportunities for unexpected discoveries. History repeatedly teaches the same lesson. Whenever humanity develops a more powerful instrument, nature surprises us. Galileo discovered moons orbiting Jupiter. Hubble revealed countless galaxies. Radio telescopes uncovered pulsars. X-ray observatories detected black holes. Gravitational wave detectors confirmed Einstein's predictions a century later. The next great surprise may already be waiting. Perhaps involving the multiverse. Perhaps something entirely unforeseen. Yet even if compelling evidence eventually appears, another fascinating question remains. How has the idea of parallel universes influenced human culture? Long before physicists discussed inflation or quantum mechanics, writers imagined alternate realities. Today, the multiverse has become one of the most popular themes in modern entertainment. Why does this idea resonate so deeply? The answer lies not only in science, but in the stories humanity tells about itself. Part 8. Long before physicists debated eternal inflation, before quantum mechanics challenged our understanding of reality, and centuries before the word multiverse was ever spoken. Writers were already imagining other worlds. Human imagination has always traveled farther than technology. Every generation has dreamed of stepping beyond the familiar, into hidden kingdoms, parallel realities, alternate histories, impossible worlds. Science eventually provided new language for these ideas. But storytelling came first. One of the earliest literary journeys into alternate realities appeared in the 19th century. In Lewis Carroll's Through the Looking Glass, Alice steps through an ordinary mirror into a world where logic behaves differently. Time moves strangely. Language twists upon itself. Reality follows unfamiliar rules. Although intended as fantasy rather than science, the story introduced readers to one of literature's enduring themes: crossing from one reality into another. Around the same period, H.G. Wells revolutionized speculative fiction. His novels explored invisible men, alien invasions, genetic engineering, time travel. Although Wells focused more on the future than parallel universes, his scientific approach inspired generations of writers to treat extraordinary ideas as logical possibilities rather than pure magic. By the early 20th century, science fiction began expanding rapidly. Authors imagined alternate Earths, parallel dimensions, different histories, entire civilizations developing under different circumstances. These stories often reflected contemporary scientific ideas. As physics evolved, so did fiction. During the 1940s and 1950s, the golden age of science fiction introduced increasingly sophisticated concepts. Writers such as Isaac Asimov, Robert Heinlein, Arthur C. Clarke, and others explored humanity's place within an immense universe. Although their stories differed greatly, they shared a common belief: science itself could inspire wonder, not merely fantasy. The idea of parallel universes truly flourished during the second half of the 20th century. Comic books became one of its most influential homes. In 1961, DC Comics introduced the concept of Earth 2. Readers discovered alternate versions of familiar superheroes. Different histories. Different outcomes. Heroes who lived separate lives while remaining recognizable. Eventually, the idea expanded into the famous Crisis on Infinite Earths, where countless parallel worlds collided in one of comic book history's most ambitious storylines. Marvel Comics later developed its own vast multiverse. Each universe received its own numerical designation. One Earth became home to the familiar Avengers. Another followed dramatically different events. Alternate versions of Spider-Man, Captain America, Iron Man, Doctor Strange. Countless possibilities unfolded across parallel realities. These fictional universes introduced millions of readers to multiverse concepts decades before they became widely discussed in popular science. Hollywood soon followed. Films embraced alternate timelines with enthusiasm. In Back to the Future, Marty McFly's actions reshape history, producing dramatically different futures. Although the film does not explicitly describe branching universes, its logic closely resembles later multiverse ideas. The Terminator series explored changing timelines and paradoxes. Characters attempted to alter humanity's future. Each decision raised questions about fate, free will, and causality. Could history truly be rewritten? Or was every attempt already part of history itself? Television also embraced parallel realities. Series such as Sliders imagined travelers moving between alternate Earths. Each world differed because history had unfolded differently. One Earth remained ruled by the British Empire. Another experienced different technological revolutions. Another never fought certain wars. The possibilities seemed endless. In the 21st century, the multiverse entered mainstream cinema. Marvel Studios introduced audiences to branching realities through films such as Doctor Strange in the Multiverse of Madness and Spider-Man: No Way Home. Characters from different universes encountered one another. Distinct histories collided. The concept reached audiences numbering in the hundreds of millions. At roughly the same time, another film approached the multiverse from an entirely different perspective. Everything Everywhere All at Once. Rather than emphasizing superheroes or cosmic battles, the film explored identity, family, regret, choice, the countless lives a single person might have lived. It became both a critical and commercial success, winning numerous Academy Awards. Its emotional power demonstrated something important. The multiverse is not merely about physics. It is about possibility. Another animated series took an even more humorous approach. Rick and Morty introduced audiences to virtually limitless parallel realities. Some bizarre, some terrifying, some absurdly ordinary. Behind the comedy lay genuine scientific references. Quantum mechanics, Schrödinger's cat, parallel universes. The show frequently blurred the line between accurate science and playful exaggeration. Many viewers became interested in real physics after encountering these fictional ideas. Video games soon joined the trend. Players explored branching storylines, alternate endings, parallel worlds shaped by their decisions. Interactive entertainment proved especially suited to multiverse storytelling because players themselves created different histories through their choices. The internet further accelerated public fascination. Online communities debated the Mandela effect, simulation theory, quantum immortality, alternate timelines. Many discussions mixed established science with speculation, sometimes responsibly, sometimes not. This created both opportunities and challenges. On one hand, millions of people became interested in cosmology and quantum physics. On the other, genuine scientific theories were often confused with unsupported claims. One recurring misconception involves the idea that quantum mechanics proves every fictional multiverse story. It does not. While some interpretations of quantum mechanics involve branching realities, they do not imply easy travel between universes. Nor do they suggest that every imagined scenario exists exactly as portrayed in films. Entertainment naturally simplifies complex ideas. Its goal is compelling storytelling rather than scientific precision. Yet fiction performs another valuable role. It encourages imagination. Many scientists first became interested in physics after reading science fiction. Some were inspired by Star Trek. Others by 2001: A Space Odyssey. Others by comic books or classic novels. Imagination often precedes discovery. Jules Verne imagined submarines before they became practical. Arthur C. Clarke described communication satellites long before they orbited Earth. Science fiction has repeatedly inspired real engineering. Perhaps one day, stories about the multiverse will similarly inspire breakthroughs we cannot yet imagine. Still, one important distinction remains. Science asks what is. Fiction asks what could be. Both are valuable, but they serve different purposes. The multiverse occupies a unique position because it exists in both worlds simultaneously. It is a subject of serious mathematical research, and one of the greatest storytelling ideas ever conceived. Yet after exploring mythology, philosophy, cosmology, quantum mechanics, inflation, string theory, and popular culture, one final question remains. What can we honestly conclude? Does the multiverse actually exist? Or is it simply one of the most beautiful ideas modern science has ever imagined? The final chapters bring together everything we have explored, separating what we know from what we suspect, and from what still lies entirely beyond our understanding. Part 9. After decades of research, hundreds of scientific papers, powerful telescopes, particle accelerators, and some of the most sophisticated mathematics ever developed, one question remains. Does the multiverse actually exist? The honest answer may surprise you. We simply do not know. That uncertainty is not a weakness. It is the foundation of good science. Science does not begin with certainty. It begins with questions. The multiverse is one of the greatest unanswered questions in modern physics. Some of the world's leading scientists believe it may be real. Others remain unconvinced. Both positions are supported by thoughtful arguments. To understand why, let us examine the strongest evidence on both sides. One of the most compelling arguments for the multiverse comes from cosmic inflation. Inflation successfully explains several major features of our universe. Its predictions closely match observations of the cosmic microwave background. Many versions of inflation naturally produce eternal inflation, in which new bubble universes continue forming forever. If inflation is correct, and if eternal inflation accurately describes nature, then a multiverse may be unavoidable. Notice the careful wording. The multiverse is not being added as an extra assumption. It emerges naturally from the mathematics. This is one reason many cosmologists take the idea seriously. Another argument comes from quantum mechanics. The equations describing quantum systems work extraordinarily well. The question is how those equations should be interpreted. The many worlds interpretation removes the mysterious process known as wave function collapse. Instead of probabilities collapsing into one outcome, every outcome occurs, each within its own branch of reality. Many physicists admire the mathematical simplicity of this interpretation. Others prefer different explanations. Importantly, current experiments generally cannot distinguish between them. At present, many worlds remains an interpretation rather than an experimentally confirmed fact. Then there is string theory. Although still awaiting direct experimental confirmation, string theory predicts an enormous landscape of possible universes. Combined with eternal inflation, this framework naturally produces countless universes possessing different physical constants. Again, this is a mathematical consequence, not an observational discovery. Together, these three areas, inflation, quantum mechanics, and string theory, provide the strongest theoretical support for the multiverse. Now let us consider the opposite perspective. Many respected physicists remain skeptical. Their concerns are not based on closed-mindedness. They arise from the scientific method itself. One criticism involves testability. Science advances through observation and experiment. If another universe can never be observed, can its existence ever be confirmed? Some researchers argue that theories predicting forever unobservable universes stretch the definition of science itself. Others disagree. They point out that indirect evidence often leads to important discoveries. No one had seen a black hole when Einstein first predicted them. Yet decades later, observations confirmed their existence. Perhaps the multiverse will follow a similar path. Or perhaps it will not. Another criticism concerns Occam's razor. This philosophical principle suggests that, when several explanations fit the evidence equally well, the simplest should generally be preferred. Do we really need countless invisible universes to explain our observations? Or will future discoveries reveal a simpler explanation? No one knows. History offers examples supporting both possibilities. Sometimes reality proves surprisingly simple. Other times, nature turns out to be far stranger than anyone imagined. There is also the danger of confusing mathematical possibility with physical reality. Mathematics often permits many elegant solutions. Nature does not necessarily realize all of them. For example, Einstein's equations allow several unusual space-time geometries. Some almost certainly never occur in our universe. Likewise, not every mathematically consistent multiverse model must correspond to reality. The universe chooses only one history. Or perhaps many. The challenge is determining which. Another fascinating discussion involves fine-tuning. Scientists have noticed that many physical constants appear remarkably well suited for life. Gravity, the strength of electromagnetism, the masses of elementary particles. Small changes in these values might prevent stars from forming, or chemistry, or complex life. Why do these constants possess exactly the values they do? Some researchers argue this supports the multiverse. If countless universes exist with different constants, observers naturally arise only in those compatible with life. Others reject this reasoning. They suggest future physics may eventually explain why the constants possess their present values without invoking multiple universes. Again, the evidence remains inconclusive. Perhaps the most important lesson is this: the multiverse is not one single theory. It is a family of ideas. Some arise naturally from cosmology, others from quantum mechanics, others from mathematical physics. Accepting one version does not require accepting them all. Each must ultimately stand upon its own evidence. Throughout the history of science, extraordinary discoveries have repeatedly transformed humanity's view of reality. Earth was not the center of the universe. The Milky Way was not the only galaxy. Time proved flexible. Space could curve. Black holes existed. Gravitational waves crossed the cosmos. Every generation has discovered that reality is larger than previously imagined. The multiverse may represent the next great expansion. Or it may prove to be a fascinating detour leading toward an entirely different understanding of nature. Either outcome would deepen human knowledge. One encouraging aspect of modern science is its willingness to revise ideas. Scientists become attached to evidence, not conclusions. If tomorrow's observations contradict today's theories, the theories change. That willingness to change distinguishes science from belief systems that resist new evidence. The multiverse will ultimately be judged the same way: by observation, by experiment, by careful reasoning, not by popularity, not by wishful thinking, not by fear of unfamiliar ideas. The search continues because the question itself remains worthwhile. Could our universe be only one among countless others? Could reality be vastly larger than we currently imagine? These questions push science toward new discoveries. Even if the multiverse itself proves incorrect, the search may uncover something equally profound. History often works that way. Researchers looking for one answer frequently discover another entirely unexpected. The final chapter asks perhaps the biggest question of all. What does the multiverse mean for humanity? For philosophy? For religion? For our understanding of reality? And if another universe truly exists, will we ever know for certain? Part 10. Stand outside on a clear night. Look toward the stars. At first, they seem peaceful, quiet, unchanging. Yet every point of light represents a sun. Many possess planets. Some may harbor life. The universe already stretches beyond ordinary imagination. And still, modern physics asks us to consider something even greater. What if all of this, every galaxy, every star, every planet, every civilization, is only one small part of a reality far larger than we can perceive? It is one of the most breathtaking ideas ever proposed. Whether it ultimately proves correct or not, the multiverse has fundamentally changed the way many scientists think about the cosmos. Throughout this journey, we have explored the remarkable path that led to this idea. We began with humanity's oldest stories, ancient myths describing hidden realms beyond ordinary perception. We followed philosophers who wondered whether countless worlds might exist, long before telescopes revealed the vastness of the heavens. We watched astronomy transform our understanding of the universe. The Earth became one planet among billions. The Milky Way became one galaxy among hundreds of billions. The observable universe expanded beyond anything earlier generations could have imagined. Then came Einstein. His theories reshaped space and time. Quantum mechanics revealed a microscopic world stranger than anyone expected. Cosmic inflation suggested that our universe may be only one bubble within an endless cosmic ocean. The many worlds interpretation proposed branching realities born from quantum events. String theory hinted at an enormous landscape of possible universes. Each step expanded reality further. Each discovery reminded humanity of the same lesson. Nature is under no obligation to match our intuition. Again and again, the universe has proven stranger than common sense. Yet science has also taught us another lesson. Extraordinary ideas require extraordinary evidence. The multiverse remains one of the most fascinating hypotheses in modern physics. It is not an established scientific fact. No telescope has photographed another universe. No spacecraft has crossed into another reality. No experiment has directly demonstrated that alternate universes exist. That distinction matters. The beauty of an idea does not guarantee its truth. History is filled with elegant theories later replaced by better ones. It is also filled with ideas once dismissed as impossible that eventually became accepted science. The future alone will determine which category the multiverse belongs to. One of the most remarkable aspects of this subject is how it unites so many different fields: astronomy, cosmology, quantum mechanics, mathematics, philosophy, even psychology. Each contributes part of the puzzle. Few scientific questions have inspired such wide-ranging discussion. Perhaps because the multiverse is about more than physics. It is about possibility. It asks us to imagine that reality may be vastly larger than our experience suggests. It challenges our understanding of identity, choice, chance, and existence itself. If countless universes exist, then somewhere, perhaps, another civilization looks up at its own night sky asking the same questions. Perhaps another version of humanity developed different sciences, different languages, different histories. Perhaps life never emerged there at all. Or perhaps entirely different forms of intelligence evolved beneath unfamiliar stars. These possibilities remain speculative. Yet they inspire wonder. Wonder has always been one of humanity's greatest strengths. Every major scientific revolution began with curiosity. Someone asked a question others considered impossible. Could Earth move? Could invisible forces shape the universe? Could time slow down? Could gravity bend light? Could black holes exist? Could planets orbit distant stars? The answer, again and again, was yes. Not because people wished it to be so, but because evidence eventually revealed a deeper reality. Perhaps the multiverse represents the next chapter. Perhaps it does not. Either outcome will teach us something profound. If future observations support the multiverse, our understanding of existence will expand beyond anything previous generations imagined. If future discoveries reveal another explanation, science will have moved closer to truth through the same process. In either case, knowledge advances. That is the true strength of science. Not certainty, but continual improvement. As technology evolves, humanity will build more powerful telescopes, more sensitive gravitational wave detectors, larger particle accelerators, new quantum instruments. Each generation will observe farther, measure more precisely, ask better questions. The universe still contains countless mysteries. Dark matter, dark energy, quantum gravity, the origin of physical laws, the nature of consciousness, the ultimate fate of the cosmos. The multiverse stands among these great unanswered questions. Perhaps future scientists will solve it. Perhaps they will discover an even greater mystery hiding behind it. History suggests the second possibility is surprisingly common. Every answer tends to reveal new questions. That endless pursuit defines science itself. The multiverse also teaches something deeply personal. Every human life contains unrealized possibilities. Roads not taken. Dreams postponed. Decisions that changed everything. Whether or not alternate realities truly exist, reflecting upon them reminds us that the choices we make today shape the only universe we know with certainty. The future remains unwritten. Every generation helps create it. In that sense, each of us participates in building tomorrow's reality. Perhaps that is the greatest lesson of all. Reality is not only something we observe. It is something we continually explore, question, and strive to understand. The search for the multiverse is ultimately part of a much older human journey. The desire to understand where we came from, where we are going, and whether the universe is even more extraordinary than it appears. As long as humanity continues looking toward the stars, building new instruments, testing bold ideas, and refusing to stop asking questions, that journey will continue. Whether there is one universe, or infinitely many, the greatest frontier has never been the edge of space. It has always been the edge of human knowledge. And somewhere beyond that horizon, the next great discovery is waiting. Perhaps it will reveal another universe. Perhaps it will reveal something even more astonishing. Until that day arrives, the mystery remains. The questions remain. And so does the wonder. Because every great scientific adventure begins with a single thought. What if reality is far bigger than we have ever imagined?